This is the notes for section 9.6, logarithmic scales. If you haven't done so already, make sure you pause the video at this time and read the section before continuing on with these notes. In this section, what we're going to do is we're going to look at a couple different scales that use logs. So we call them logarithmic scales. We're going to first look at the decibel scale. The decibel scale is basically a way that we can measure the relative sound intensity. Okay? Sound intensity in terms of with units would be measured in watts per square meter. Okay, watts is kind of, if you think about your stereo, what it puts out is it's measured in watts. Well, it's measuring how many watts we have in a square meter. Okay, so that range is very, very large. It goes from barely audible to 10 to the negative 12th power, all the way up to, you know, higher than a jackhammer, which is 10 to the second power. Okay, so in order to kind of make that a little bit more readable or easier to understand, we use the logarithmic scale to kind of condense that a little bit. And by doing that, you can see the relative intensities in decibels listed over here on the right hand side. Okay, well, we have a formula that we can use for working with the relative intensity in decibels. Okay, and that formula relates the sound intensity N. So N represents that sound intensity, which is this number right over here in watts per square meter, and we rate it to its relative intensity in decibels. So D is the number of decibels, N is the sound intensity. Okay, in general, and this is, I have this in bold because you're going to need to be able to use this in a number of different problems here. In general, an increase of N decibels multiplies the sound intensity by 10 to the N over 10. So let's take a look at example 1 here. It says music played at 125 decibels is how many times as intense as music played at 105 decibels. Well, to figure out the how many more times intense it is, we're looking at this idea right up here, in that the decibels is, and if it's an increase of n decibels, we're going to increase it. The intensity is 10 to the n over 10. So what I'm going to do is I'm going to look at the difference between our decibel levels, excuse me, 125 and 105. That means it was an increase or difference of 20 decibels. Okay? So if that's what N is, to find that increase or how much more intense it is, I'm going to take 10 to the 20 over 10, which is equal to 10 to the second power, which is equal to 100. Therefore, it's 100 times as intense as the lower level music. So it's 100 times louder than at 125 decibels than it is at 105 decibels. Let's take a look at example 2. We're going to use the same logarithmic scale to do this one. It says find the relative intensity in decibels of a muted conversation in which the sound intensity is 3.16 times 10 to the negative 8th watts per square meter. Okay, so if that represents my watts per square meter, that's the value I'm going to put into my equation for N, and I'm trying to find D, the decibel level. So I'm going to plug this into my calculator with, instead of N, I'm going to put in 3.16 times 10 to the negative 8th power. If I do that, okay, and then I'm going to come over to my calculator and I'm going to enter that there, we get a value of about 45, roughly 45 decibels for my value there. So over here I'm going to put my D value is equal to 45 decibels. So let's take a look at example number 3 here. It says a very loud rock band plays at a relative intensity of 125 decibels. What is the sound intensity in watts per square meter? Well, to do that, I'm going to use this equation, but instead of putting in something for n, because that represents the watts per square meter, I'm going to put 125 in for the level D. So I can say 125 is equal to 10 times the log of n over 10 to the negative 12th power. Okay, so now I got to solve for n. Well, to do that, I'm going to kind of undo everything that's being done to n, and the first thing I need to undo is I need to get rid of that 10. So I'm going to divide by 10 on both sides. So I have 12.5 is equal to the log of n over 10 to the negative 12th power. Now I've got to think about, remember we can write logs in both exponential form and in logarithmic form. Well, I'm going to change this from exponential or from logarithmic form to exponential form. Remember, this is like having a base of 10, so I can say 10 to the 12.5 is equal to n over 10 to the negative 12th power. So I'm getting close now, so I got to get rid of this 10 to the negative 12th power. So what I could do is I can multiply both sides by 10 to the negative 12th power. Okay. If I do that and I use what I know about exponents, the negative 12 plus 12.5, if I add those exponents together, I get 0.5. So I can write this as 10 to the 0.5. This is going to cancel with this, is equal to n. So n is approximately 3.16. The second logarithmic scale we'd like to take a look at here is the earthquake magnitude scales, and we call that the Richter scale. You probably heard that term before used, whether it be on the news or when you've heard or read about earthquakes. That value, a value on the Richter scale, x, okay, corresponds to the measured force or the amplitude of k times 10 to the x, okay, where the x, once again, x is the value on the Richter scale. So this value right here, this x, that's the Richter scale value. The constant k depends on the units being used to measure the quake. Okay, so here's a chart of kind of what happens for different level magnitudes of earthquakes. So, you know, the difference between a 5 and 7 doesn't seem that much, but a 5 just is strong enough to wake sleepers, whereas a 7, the ground cracks and houses collapse. So that's how we kind of deal with the Richter scale, and it is a logarithmic scale. So let's take a look at example 4 then. It says on May 12th in 2008, the Sichuan province in China was hit by an earthquake that registered 7.9 on the Richter scale, and a deadly tsunami that struck 12 Indian Ocean nations in December 2004 was triggered by an earthquake of 9.3 on the Richter scale. The force of the 2004 quake was how many times the force of the 2008 quake? Okay, so what we're doing is we're going to take a look at each of those values. So if I'm thinking about the heavier one, the 9.31, I'm going to say that's k times 10 to the 9.3 power. Whereas the lighter one is k times 10 to the 7.9 power. Okay. Well, in both cases, it doesn't matter what units we're measuring this in. Those k values are going to cancel out. So I'm really left with 10 to the 9.3 over 10 to the 7.9. I can subtract the exponents there, and if I do that, I get 1.4. So that's the same as 10 to the 1.4. So that would be, that's how much more intense the earthquake in 2004 1.4 was than the earthquake in 2008. So that's approximately equal to 25 times as intense. Okay, if we look at that on our calculator, if I take 10 to the 1.4, I get just a little bit over 25. So it'd be approximately 25 times as intense.